everybody. It's a pleasure to have Alberto Chiarini with us today from Padova, and he will tell us about how efficiently a simple random walk covers a portion of the macroscopic value.
Thank you very much for the invitation. Speaking here today. So today we'll speak about joint work with Maximilian Nitzschner, who was previously at NYU Courant and recently started a new job in Hong Kong at the University of Science and Technology. So today I will try to answer the following question: how efficiently does a simple random walk cover a portion of a macroscopic body? It's kind of a classical question, and hopefully it will be an interesting answer. So we start immediately with the model and try to figure out this question. So we have a simple random walk on the Euclidean lattice, ZD. Let's denote the range of this random walk by this set, range. This is the set of all points visited by the simple random walk. It's the set in red over here. And then we have a macroscopic body, Bn, and it's macroscopic because its size, it's increasing with n. You can think equivalently that we are making the grid smaller with a parameter 1 over n. Well, this is a blow up of the macroscopic body, B contained in Rd. Now we look at the number of points covered by this simple random walk, and we want to cover a fraction of points, and we denote by me the fraction of points that we want to cover. Now, if we are in dimension 1 and 2, there is no real question. If we look at a random walk starting from the origin, and we look at the range intersected with this macroscopic body, then it will cover all of the set, because the random walk is recurrent. So this probability is equal to 1 in dimension D equal 1 and 2. The random walk will cover all of the set, no matter how small it's the fraction, how large is this fraction. When the dimension D is greater or equal than 3, this becomes a rare event, and the probability goes to 0. And what we want to do today, this is the goal of today, is to estimate the probability that we cover such a portion of a macroscopic body, and we want to give precise large deviation estimates for the event in dimension D greater or equal than 3. And then we want to understand how does the random walk look like conditioned on this deviant behavior that is of covering the set, this macroscopic body quite consistently. So if we, here I have a picture in dimension 2. So what we want to do is to cover a macroscopic fraction of this body. Well, if you want to reach such a situation and we zoom in, what we will see for the random walk condition of covering a positive fraction of this body is some atypical high density regimes, and the random walk will look like globally recurrent inside these mesoscopic boxes, but locally transient, because the geometry of the lattice is still the geometry of ZD, D greater or equal than 3, but the random walk needs to come back many times in order to fill this setup. And so if we are in such a situation where we have a typical high density regime, what I want to show to you today is that the random walk locally looks like random interlacements. And we will be able, yes?
Alberto, also, just at the heuristic level, is there a simple argument why it should actually look like a random interlacement.
At the heuristic level, I mean, I will come back to that. This
Okay,
is
perfect.
all what the talk is about, finally.
Okay, thank you.
So the talk about today is about this relation between random interlacements and a random walk, and how to use random interlacements to derive quantitative and precise large deviation estimates for this kind of events. So locally, it will look like random interlacements, and I will come back to that later. A first answer for this question comes from Asela and Shapira, 2022, and they look at the probability of covering many sets, many balls, with a positive fraction. And they show that some quantitative estimate for this probability, that the random walk, the range of the random walk covers a positive fraction of each one of these balls here. And the nice thing about this result is that it is non-asymptotic, but they get some nice constants, the fraction here. And the other important fact is that this probability goes to zero exponentially fast and with a rate which is of capacity order. Now, this result is nice because it's non-asymptotic, but what we are looking for today is to give a precise asymptotic rate for the probability. So we want to identify the exact constants when in the large deviation regime. A similar situation, it is similar because it has kind of the same features, both in the proofs and in the behavior, is that of disconnection by random walk. So suppose that we have again some macroscopic body that is the blow up of some subset of RD, still D greater or equal than 3, and then one might ask, let's start a random walk from 0, and I want to disconnect this set Dn from infinity. So think about this random walk as a termite is eating out some wood, and you want to disconnect some macroscopic body from infinity. And you could ask what is the chance for the random walk to disconnect the n from infinity. Again, this will go to 0 exponentially fast. And in order to achieve such a behavior, to disconnect this set, we will need to achieve some atypical high-density regimes around the boundary of this set Dn. And what turns out the case is that at the mesoscopic scale, the random walk will look like random interlacements with some particular density, intensity. So this, the study of disconnection by random walk was done by Sznitman in 2014, where he gave an asymptotic upper bound for the probability of disconnecting such macroscopic body from infinity. And Xigny completed the analysis with an asymptotic lower bound. And in both cases, random interlacements appear as a crucial tool to understand the picture. So I want to speak a little bit about random interlacements for those of you who don't know it. And then I will come back to how this connects to the problem of today. So random interlacements, they start with a model, as a model by Hilhorst for corrosion. And Hilhorst was imagining the simple random walk as some corrosive particle and wandering about, and the set of points visited by the random walk was said to be the set of corroded points. And one of the initial questions was how long does it take for a material that is corroded by a simple random walk to become brittle, to become disconnected? this is the model that was proposed. We have a d-dimensional torus, Tn. We still are in dimension d greater or equal than 3, and the n is the side length of the torus. And then we look at a simple random walk started at equilibrium and its range, the set of points visited. These are the corroded points. Well, if we now look at some subset of this torus, for example, this K in the picture, and we look for n large, so that K is completely contained in the set, then the probability that the range does not intersect the set K is roughly equal to 0 if the walk runs for a long time, and it is roughly equal to 1 if the walk runs for a short time. The interesting fact is that there is an interesting regime when the range is up to time, which is of the order of the volume of the torus. In this case, we have a non-trivial probability appearing. Also, why is this situation similar to what we were looking before? Because in the torus, we have a geometry where the random walk is recurrent, but it is locally transient. The geometry, the local geometry that the random walk sees is that of ZD with D greater or equal than 3, but globally is coming back many times. Okay. So the interesting regime is that we let the random walk run for a proportional to the volume of the torus. And if we do so, then the probability that the range of the walk does not intersect a subset K as a limit as the size of the torus goes to infinity. And it is exactly given by exponential minus u, where u is the proportionality constant, times the capacity of the random walk of the set K, where the capacity of K is some sort of measure of K as seen from a random walk started at infinity. You can think about it as follows. And here you see some pictures of this torus and the random walk that is eating out the material. The red component is the largest connected component of what is left over so it's the complement of this the points visited, and the blue is the second largest connected component. So you see, when we vary the intensity, this proportionality constant, there is an abrupt change in behavior between a situation where the largest connected component is essentially everything, so everything is well connected, and a situation where everything is pretty much disconnected. So one might be interested now to understand this question of corrosion, to see whether there is a phase transition between a situation where everything is well connected and everything is pretty much disconnected. Okay. And one way to answer this question is that of introducing random interlacements. And the random interlacement set, this is a first definition, is kind of capturing the leftover set by a random walk on the torus when we make n go to infinity, the side length of the torus. So the random interlacement set is a random subset of ZD, and it is characterized by the following property, that the probability that the random interlacement set intersect a set K does not intersect the set K is exactly equal to exponential minus u capacity of K for all K subset of ZD finite. So you see that this characterization comes exactly from this picture that the random interlacements should capture the trace left by a random walk on the torus that runs up to a time u times the volume of the torus. Should capture this picture. One interesting thing is that this interlacement set, this is a random subset of ZD, has polynomial decay of correlations. And the other interesting thing is that the law of this interlacement set is translation invariant, ergodic, and satisfies FKG inequality. So we have an object that is global, defined on the whole ZD, that captures the local picture by a simple random walk on the torus.
I have a question.
Yes.
At the top of your in the definition, do you mean there's nothing asymptotic about that? There's no limit.
There's nothing asymptotic. The asymptotics is here. So if we let n to infinity, we get exactly this expression. And you define the random interlacements as a random subset of ZD for which this is true. So this is a random subset of ZD, of the whole lattice now. And it is meant exactly to capture this picture. I will give a more constructive definition in a second.
Okay, good.
Really by random walks, so it will be more clear. So what you can show is that a probability measure that satisfies this property exists, and so this is, of course, and the idea is that this comes from the torus, but from this picture that I gave before, but I will give a more constructed definition now. This is a first, say, definition, which is useful because it already gives you some nice properties, such as polynomial decay of correlations and translation invariance, ergodicity, and FKG inequality. A more constructive definition, I give it now. And the one way to construct this random subset of ZD, this interlacement set, is as follows. I consider the harmonic measure of set K, this is my K, and I consider the harmonic measure on the boundary. This is just a probability that the random walk does not come back to K if started from the boundary. Then this defines a measure on the boundary, and the capacity is just the total mass of this measure. Okay. Now, how do I sample random interlacements inside K? I do it in two steps. First, I decide the number of trajectories. The number of trajectories given by a Poisson random variable with intensity U times the capacity of the set. And then once I decided how many trajectories I want, I sample n copies, n IID simple random walks, according to, started from the boundary according to the harmonic measure. And then if I want to know what is the distribution of this random subset of ZD inside K, this is just the union of these ranges intersected with K. So for example, I sample n equal 2 for my Poisson random variable. Then I start two independent random walk, 1 and 2. And what the intersection of the trajectories of these two walks with K is the interlacement set in K. So there is this idea of coming back many times, and that's why I have the harmonic measure here. This gives the local picture of random interlacements. There is also a way to give a global picture as a Poisson cloud of random walks. So one defines a Poisson point process of trajectories. I'm not going into detail into that, but one can define the random interlacements measure as a Poisson point process of trajectories with labels, and the labels are there to couple all interlacement sets with varying intensity. And with this is a Poisson point process with an intensity that is constructed in such a way that it is consistent with the local picture. This is possible, and then so we have this Poisson point process of trajectories in the space of nearest neighbor paths that come from infinity and go to infinity, and the positive real line. This is for the labels. And then we have these points, and the random interlacements below at level U will be given by such points. Each point is a trajectory. This is the green point. And if we increase level, we are just throwing more and more trajectories. Why I tell you this? Well, it is interesting that there is such a global picture. One important thing is that in this Poisson point process construction, one of the power is that if I increase the level, this just accounts as throwing more trajectories. So I have a nice coupling between all the possible levels. Okay. So coming back to the question of corrosion by simple random walk, so we saw that there was this there was this abrupt change in behavior when the proportionality constant U was small and when U was large for the random walk on the torus. So, and in order to answer that question for the random walk, we first look at a similar question for random interlacements. So one is interested when looking at random interlacements set at the vacant set, at the set of points that are not visited by random interlacements. So this is the leftover set. And if we increase the level of the intensity of this interlacement set, we are just throwing more and more trajectories. So the vacant set is becoming thinner and thinner. And so the question arises whether there is a phase transition in the percolation properties of this vacant set. And such a phase transition is there, and it is non-trivial. So there exists some parameter U star, which is strictly positive and finite, such that the probability that the vacant set has an infinite kinetic component is equal to 1 if U is smaller than U star, and it is equal to 0 if U is bigger than U star. Recently, this is really a result of this year, and it's a highly non-trivial and very important. It has been proven that the transition is sharp by Dumilil Kopang, Goswami, Rodriguez, Severo, and Teixeira. And this has important consequences also for what I'm going to say in a second. So what about the random walk and the corrosion? So Teixeira and Windisch in 2011 showed that for all U bigger than U star, and the important point is that this U star is the one coming from random interlacements. For all U bigger than U star and any eta bigger than 0, if we look at the biggest component of the leftover set by the simple random walk on the torus, up to time U to the n to the t, then the probability that we have a macroscopic component, so the size of the biggest component is bigger than eta n to the d, goes to 0 as n goes to infinity. And not only that, now that the sharpness of the phase transition has been established, one can also give even a finer characterization, saying that when U is bigger than U star, there are only small components. And when U is smaller than U star, the biggest component has a macroscopic size, and it is exactly given by n to the d times this quantity. The crucial takeaway point of this slide is that we started from a question that was about the simple random walk, and that is how long should we run simple random walk on the torus until the material becomes disconnected. And we gave an answer, finding a precise result where the constant, the important constant, comes from the random interlacements objects. Okay. And also
question is there, what do we know about U star? Is it 7 or are there bounds?
Okay.
Sorry.
It exists. It exists. It is positive. It is finite. There are some asymptotic with the dimensions. But I don't remember them exactly.
But it depends on dimension, of course.
Depends on dimension, of course.
Thank you. Good.
So the takeaway is that in these high density regimes, the random walk is well captured by random interlacements, and one can use random interlacements to identify important quantities. Okay, after this brief excursus in the random interlacements business, let's come back to the problem I stated in the beginning of the talk. So we have some subset of RD. Then I take its blow up by n. So I multiply by n and intersect with ZD. If you like the other picture, you can think about, we are just making the grid smaller and smaller. Then we also have some Ni, that is the fraction, the fraction of points that we want to cover. And what we want to do is to find precise large deviation asymptotics for the probability that the range of the random walk intersected Dn, this macroscopic box, is Ni fraction is at least Ni times the size of Dn. So we want to visit a fraction, at least Ni of points of this macroscopic set. In order for the random walk to do that, it needs to realize a typical high densities. And the idea is to study first the large deviations for the event that the random interlacement set realizes these atypical high densities. And then maybe if we send U to 0, so the intensity is to 0, we are left with only one trajectory, and we will also obtain an answer for the simple random walk. Let's see the thing for random interlacements first. So here I'm just repeating, I have a subset of RD, open bounded, regular enough, and U is some intensity for my random interlacements. And Dn is the blow up. And then if I look at the number of points covered by random interlacements inside this set Dn, it is just this quantity here. It's a nice sum. And remember that the interlacement set measure is ergodic stationary. So this is one of the nicest thing about it. And so the ergodic theorem tells me that I will touch a fraction of points, which is given by the probability that 0 belongs to the interlacement set at the level U. And for this, we have formulas. It's 1 minus E to the minus U times the capacity of one single point, which is 1 over the Green function at 0. Just to say that this is a precise quantity. So we found this precise quantity, and we look for excess deviation with respect to this expected behavior, this expected density. So we take a fraction of points that we want to cover, which is strictly bigger than this expected density, and we want to quantify large deviation asymptotics of the probability that random interlacement sets cover a fraction of points that it is bigger or equal than me. which is bigger than the expected density it would cover. Okay. This is a question that was answered by Sznitman in 2019. And he showed that for all ni between 1 and this quantity, which I define like theta u, it's a function of the intensity, the probability that the interlacement set covers a fraction nu of points of a macroscopic body decays exponentially fast with a speed that is of capacity order, so it is n to the d minus 2, and with a rate which is given precise by the following variational problem. It's a rate which is found by minimizing the Dirichlet energy of functions phi that are smooth and non-negative, and such that the average of theta computed in square root of u plus phi square is bigger than nu. One interesting thing is that there exists a minimizer for this variational problem. And the minimizer doesn't need to be in L2, but it is in the space of function with finite Dirichlet energy that is vanishing at infinity. Okay, what is going on? So how does this random interlacements achieves this deviant behavior? To find out that, it's typical in large deviations. We look at the minimizer of the rate of this rate. And the deviant behavior is realized by tilting the trajectories. So we add to each trajectory a certain drift to make the trajectory spend more time inside the set dn. And each trajectory that was a random walk trajectory is replaced by a tilted random walk, where the tilting is given here, where u is a minimizer. This adds effectively a drift that makes the random walks spend more time inside this set. Okay. So this was for the random interlacements. We have this nice large deviation asymptotic. And what about the random walk? Well, one interesting fact is that at least to get an upper bound, it is enough essentially to send the parameter of the intensity to 0. Because the random interlacement sets contains random walk trajectories. So at least to give an upper bound, we can derive it immediately from Sznitman, result for random interlacements. And so for every possible ni in 0, 1, one gets that the probability that a simple random walk covers a fraction of points nu of the macroscopic body decays exponentially fast with a speed that is of capacity order, n to the d minus 2. This is due to these long-range correlations, polynomially decay correlations of this model. And then we have this rate, this precise rate, where the rate is just, again, coming from a variational problem, is the smallest Dirichlet energy, where u is the smallest Dirichlet energy constrained to functions that are non-negative, that are in this space d1, 2, and such that, see here, the average of over d of theta computed in phi square is equal to nu. And recall that this theta came from random interlacements. This theta u is just the probability that 0 belongs to the interlacement sets at level u. So what we found here is an upper bound completely described by a function, by a constraint minimization problem, where the constraint involves a function that comes from random interlacements. Okay. Let me show you the proof for the upper bound, which is very simple. It's just this idea that random interlacements contain random walk trajectories. So if we have some u positive, and we can look at the random interlacements, and we condition it to have 0 inside, so that I will have at least one trajectory that goes through 0. Okay. And so I have this random walk trajectory here, contained in the interlacement set. So if I look at the probability that for the simple random walk started at the origin, that the range covers at least a new fraction of the macroscopic body, this is bounded from above just by dominating with the interlacement set at level u, any level u, by the probability that the interlacement set covers such fraction of body, condition that 0 belongs to the interlacement set. But now this is just using the definition of conditional probability. So I take the log both sides. I divide by 1 over n to the d minus 2, and I take the limit. And you see this conditioning doesn't really play a role, because the probability that 0 belongs to the interlacement set is of order 1. And so I'm left bounding this quantity by the same quantity for the interlacement set. This argument can be made for all possible intensities u bigger than 0. One has to show that there is some continuity in u, sending to u to 0. And so you just take u to 0 and get the upper bound. As you see in the variational problem, what has changed is that instead of having here square root of u plus phi square, I just have phi square. I replaced u by 0. Okay. What we did together with Maximilian Nitzschner is to complement, and this is still is not on the archive yet. We are still writing it down. Should not take too much. Is to complement this upper bound with a lower bound, so that the exact rate is really given by this function here. So we showed that for all possible nu in 0, 1, the probability is in fact the log probability of this event divided by 1 over n to the d minus 2 converges to this exact rate. Okay. So I want to explain a little bit some heuristics on how to get this lower bound. And I wanted to explain also how does the random walk produces such a deviation. As it is typical in large deviation lower bounds, we have to come up with a strategy to realize this deviant behavior. And a strategy that is typical, that makes the deviant behavior typical. And then once we have this strategy, we can find the lower bound by entropy lower bound, by tilting the measure appropriately. So this is what I'm going to discuss now. This probably is well known by many of you, but I like it very much, and I want to tell you about that. So we consider the event that our random walk covers this positive fraction of points, and we want to show a lower bound for the large deviation lower bound for the probability of this event, an. And what we will use is the classical entropy inequality, which tells you that if I have a measure that is absolutely continuous with respect to a given reference measure, and an event with positive probability, that then the relative entropy between Q and P can be bounded from above, from below by this nice quantity. What is nice about this quantity is that in this quantity I have the log of QC and I have the log of PC. So by rewriting this nice inequality, I can bound from below the logarithm of the probability of an event C, where P is my reference measure, from below by the logarithm of the probability with respect to the new tilted measure, Q, paying some price, and the price is that of the relative entropy between the two measures, essentially. So what is then the idea? Is to use this entropy inequality and to construct a tilted measure. I call it P n tilde. This is equivalent to say to construct this tilted measure is we want to control this random walk, and we want to add a drift or control this random walk in such a way that under the new measure, the event under consideration becomes typical. So I want to construct an optimal or quasi-optimal strategy to obtain the deviant behavior. And of course, I want the relative entropy cost to be easily computable and nearly optimal. Once I do that, of course, by this relative entropy lower bound, I can control this quantity, that is the one of interest, with the same quantity for the tilted measure, and the cost is that of the relative entropy. Note that since I'm making the event typical, this quantity will go to 0, and this quantity will go to 1. And so I will get a lower bound that is just the relative entropy cost of the tilting. So what is the strategy then? The strategy, since we believe that the rate is the correct one coming from this variational problem, the nearly optimal strategies should come by taking the minimizer of the variational problem and controlling the random walk with some caveats. So we take U to be the minimizer for the variational problem. Actually, we look at the variational problem with zero boundary conditions outside a very large box for technical reasons. And then we introduce some time horizon Tn, which is of the volume order times the L2 norm of the minimizer. Okay. And then what is the optimal strategy? I will look at a random walk that is not anymore a simple random walk, but as a new generator, lnf, which is tilted by this minimizer, slowly tilted, very slowly. So that on mesoscopic boxes, it will still look like a simple random walk, but globally it will be pushed towards inside this set. So it will come back many times. And there is why we will see random interlacements. But we do that not for all times, but just up to this time Tn. Well, the problem you can understand is that if you don't release the walk after time Tn, it is just going to be recurrent, and it will cost too much. So we run the random walk up to time Tn, and then we release this control Un and let it evolve according to simple random walk. And this is our quasi-optimal strategy. for those that come from stochastic optimal control, what we are doing is just introducing essentially a control of this type, gradient log of U, where U is the minimized. Okay. So if we do that, what you can show is that the relative entropy cost for this new tilted measure is essentially the Dirichlet energy of the tilting of this drift U, and which, since U was the minimizer, is essentially the rate. We picked it for this exact reason, plus some small error. And the second thing one should show is that under this change of measure, the event becomes typical. And why is this the case? This is the case because under this new measure, and now I'm just giving an heuristic argument, under this new measure, the random walk looks like random interlacements on mesoscopic boxes. And the intensity is given by U squared rescaled by N. So it's slowly modulated. And so if you believe me that the local picture for mesoscopic boxes should be this one, then you understand that now we have a nice additive structure for which the range of the random walk intersected the N can be split in the sum over mesoscopic boxes of the range in these mesoscopic boxes. And now, since the range in mesoscopic boxes looks like interlacements at this level, then this sum is just the sum over B of interlacements at level U squared xb over N, where xb is the center of the box, intersected P. But for this guy, we know by the law of large numbers that this is essentially theta at that level. So theta U squared xb over N times B. And now this is just a Riemann approximation. And you see that this U square this U was chosen exactly such that the integral over D averaged by the volume of D is equal to nu. You get essentially that under this new measure, the range intersected Dn covers roughly ni points of a fraction of points that is nu. And so after this change of measure, we realized this typical behavior. Because this is just an heuristic. What is non-trivial is to construct the couplings to control what happens in mesoscopic, to show that this is actually going to 1. But the idea one should have is that since the walk is coming back many times, it will be interlacement sets with a certain intensity, and it turns out that the intensity is given exactly by U squared. Okay. Let me conclude just with a couple of remarks on the variational problem that are interesting and open kind of other questions. As I said, so to get this lower bound, we had to construct some quasi-optimal strategy for the random walk to realize this deviant behavior. So it's interesting to understand how these minimizer look like. If we understand the minimizer, we kind of understand also how the random walk covers these sets. Well, if we look at the minimizers of this variational problem, subject to this constraint, Then, well, there is one first question is whether there is a unique one. And this is not clear, and it's probably is not true. The other interesting features is that well, U is the minimizer is quite nice, is regular, is harmonic outside of the macroscopic set D. This just comes from first order perturbation argument of the Dirichlet energy. And since it is harmonic outside of the set D, you have that it decays like x to the power 2 to the minus d. In particular, this means that, and that's kind of interesting, that the L2 norm is infinite for this minimizer when the dimension is 3 or 4, and it is finite for larger dimensions. So if we go back to our quasi-optimal strategy, I told you that the time horizon should be n to the d times the L2 norm, essentially, of the minimizer. So we have a very different behavior in dimension 3 and 4 and 5 and higher. So you need to let the random walk run for much longer in dimension 3 and 4 than in dimension 5 or larger. And then the other interesting fact, well, is that you can rephrase this as a in PDE language, saying that the minimizer needs to satisfy this nonlinear PDE. But it is quite unclear whether the solution of this problem is unique. Okay. With that, I want to finish, and thank you very much for your attention.
It was worth getting up for. Thank you.
Thank you.
Any questions?
So I have a question. Can I ask a question? Yeah. So you minimize. Can you show it is actually continuous inside the domain the D?
Okay. I mean, the minimizer is going to be, yes. Well, outside is harmonic, so it is this infinity. Yeah. Outside of D. Inside the domain, it should be continuous, at least for this special case where we look at the fraction of points, because this theta is very regular. Mm-hmm. Theta is e to the 1 minus e to the minus u, essentially. So it should at least be continuous. But these are kind of interesting and difficult questions. I opened books in semi-linear PDEs. It's not at all clear.
I'm just asking because I mean, at least at the heuristic level, it seems to me that okay, so your condition. Basically, so you're doing this H transform, right? This is what this.
Yeah, it's an H transform essentially, yes.
Yeah. And then because the U is kind of regular around the origin, it means that the H transform is actually not doing anything at the mesoscopic level. So this is.
Yeah, essentially. So coming to that. Our quasi-minimizer is continuous, so we pick it continuous. So we can get nice infinity approximations. And that's quite important because we have to say that at mesoscopic level it's homogeneous, essentially. Yeah. Yes. The problem it's amenable. The rate function. It's continuous in Nu, for example. So some regularity is there.
Okay. Thank you.
But of course, when if you change the kind of observable, in this talk, I talked about the observable, which is a number of points, then the question is different. With Maximilian, we also look at other observables of the local time. You can look at other observables and ask the same questions. So, for example, you can take functions of the local time field of the random walk and look at the deviations of averages of this one. And the problem is exactly the same. And again, the random interlacements again enter the picture. And the function changes. Theta u is not the probability that 0 is in interlacement set. It will be something else. But it's still coming from random interlacements, the constraint. Because locally, this is what the random walk is doing, is coming back many times to have these high density regimes.
So I have a question.
Yes.
So you look some kind of at upper deviations then. So I don't know if this problem is already solved, but what you could also ask yourself, what's the probability? You look at the range of the random walk until time n, and then you ask yourself, it's a little bit larger than typical, so larger than nu times.
Yeah, this is a good question, and it connects to the Wiener sausage.
Yes, exactly. Well, yeah,
and Swiss cheese picture.
Right? Yeah, exactly.
And I think, methods. I don't know if I don't think this is answered for the random walk. It is answered for the Wiener sausage. I think the methods we have should be good also for the random walk.
Yeah.
Just for the audience, you look at the Brownian motion, and you look at the Wiener sausage. So you take a small ball around the trajectory of the Brownian motion, and you ask that the size of the trajectory enlarged by this ball covers is at most b times t, where b is smaller than the capacity of the ball. Yeah. And then here you get something similar. This is a result from Van der Berg, Bolthausen, and then Hollander that didn't know about the random interlacements at the time. And they show this large deviation principle. The major difference is that since you are going up to a certain time t or time n, as you were suggesting, then you have an extra constraint, and that's the constraint is that the L2 norm of your variational problem should be bounded by some constant. And so I see, and also they have a very different behavior, dimension 3 and 4 and 5 and higher. We do not have a constraint on the L2 norm. So because we run the random walk up to the end of time.
Yeah.
But that's kind of the difference. And they say that the Wiener sausage looks like a Swiss cheese. And so what we can, what we could do is, let me take maybe a new page, is say, well, let's try to ask the same question, but let's put more balls. Okay. The balls are at distance n from each other and are macroscopic in the sense that they have radius n. Okay. And I want to cover each one of them for a sizable portion. Each of them I want to cover a new fraction. How does the random walk look like? Well, this is nothing more, and this should be nothing more that the rate function should be minimizing the Dirichlet energy among all functions phi, such that each one of these constraints is satisfied with theta exactly as before. So for all balls. Maybe I have n balls, maybe 10 balls there. Well, what is interesting here is that then the minimizer is telling you the following. The minimizer is some positive function in each of these balls, and then you have the harmonic kind of extension outside. And the harmonic extension is not zero outside. So the random walk will of course spend a lot of time here. It will look like interlacements at some level, but also here it will spend a lot of time. It will also here look like interlacements at a lower level. So it will the picture will be very, very crowded. It's not this picture I draw here is not the good one. The good one should be that yeah, there are some smaller drift. So this is a bit less dense, and here is more dense. But it's coming back many times. So this is quite interesting indeed.
Yeah. But so you think that maybe the techniques you use could be used to prove these kind of upper deviation bounds?
Yes, I think so. Yes.
Cool. Okay, cool. Thanks a lot.
Any other question? Pablo?
Thank you, Alberto. Very nice talk and exposition. I wonder about the microscopic level. Can you show also that the condition of random walk converges to random interlacement?
At the microscopic, yeah, okay. Well, this is not my for this kind of deviations. So, well, classically, it is possible to show if you take a random walk on the torus, and then you can show yes, it converges.
Yes.
For our situation, I believe the same technique. I believe it should be possible, but I didn't do it. I can't. And it's not super clear, indeed. So what you could say is take a finite subset K, and then on each for every subset K, there it will converge to random interlacements.
Yeah, but without the drift, right?
Sorry?
With no drift.
I didn't catch that.
With no drift. No, so the interlacement will be symmetric. So.
Yeah. It's no, it's a good question. I'm not quite sure about the answer. No.
No, my question was about the H function. The H transform there will be constant, no H transform.
Yeah. On the torus, it will be constant. Yes.
Okay, thank you.
Yes.
Okay. Okay, if there are no further questions, let's thank Alberto again for a really nice talk.
Well, thank you all for inviting me, actually.
Thank you.
Thanks.
Bye.
Bye-bye. Bye-bye.
Bye-bye.
We'll meet next week. Bye.
Ciao.
Bye.
Bye.